Hello students. Today we are going to start with our next lecture. And in the last lecture, we have covered some of the topics like del. Del, that is, this one is the symbol for del, and it is also called as nabla. And the next is we have covered gradient. Okay, that is del 5. That is a simple multiplication of del with a scalar quantity, and this will result in the vector quantity. Okay, this will result in the vector quantity. And after gradient, we have covered the divergence. That is del dot a vector. Okay, here it is dot product, del dot a vector. And after solving this divergence, you got a scalar quantity. Okay, and under this, we have also covered one very important topic. Divergence in zero is called as a it is a very important because based upon this concept. So if del dot a vector is equal to 0, so this one is called as solenoidal vector. This is and after this divergence, we have covered in the last lecture, that is the curl. So what is the curl? Curl means the simple rotation of the vector. Okay, and its formula is del cross a. The result for the curl of any vector is also a vector. Okay, the result for this is a vector. And how to solve this curl? That is by taking the determinant for del and a vector. Okay, then you got the answer for the curl. And very important concept for this curl also, that if the curl of any vector is 0, so that is called as the irrotational vector. Okay, the curl, if del cross a vector is equal to 0, this represents your irrotational vector. Okay, and one thing we have also covered, that if del cross a vector is not equal to 0, okay, if del cross a vector is not equal to 0, so this is called as the vortex field. So these are some of the very important concepts, and most of the numericals are based upon that. And we have covered some numericals in the last lecture based upon these concepts also. And in today's lecture, we have to cover some of the identities based upon this del, gradient, divergence, and curl. So we have to do 2 identities. First identity is, that is the also. First identity is, that is del cross del p. Our first identity, that is del cross del p is equal to 0. We have to do the proof of these identities. Del cross del v is equals to 0. Here v is any scalar. If v is any scalar, so what does this mean? How can we write it in the words? That is the curl of gradient of any scalar is 0. Okay, this is the identity. That is the curl of gradient of any scalar quantity is 0. Here v is the 0. A scalar quantity is there. V is any scalar quantity. So let's do the proof for the first identity first. starting with the v's. What is del v? Like curly v by curly x into I cap plus curly v by curly y into j cap plus curly v by curly z into k, where I, j, k are the unit vectors. Okay, then del cross del v. Solve here the curl, so we have to solve with the help of determinant. So simply write here I, j, k. Firstly del, that is curly by curly x, curly by curly y, curly by curly z. Okay, and del v, this one, it is y and curly v by curly. Okay, now simply solve this determinant like here. Firstly, cross multiplication of this. So I cap common. Cross multiplication of this will result you del square v, curly square v, sorry, curly square v by curly y, curly z. When you multiply this with this one, so this will gives you curly square v, curly y, curly z minus curly square v, again curly y by curly y, curly z. Okay, as you notice from here that this will remain the same quantity. Okay, with the negative sign and cancel out that. Then minus j cap, again curly square v, that is curly x, curly z minus curly square v. Now this with this curly x, curly z. Okay, plus k cap, this with this, that is curly square v by curly x, curly y minus curly square v is with this curly x, curly y. Okay, and as you see here that these comes out to be the same quantities, so these cancel out with each other like this, and it will give you a 0 I cap plus 0 j cap plus 0 k cap. We don't write it as directly 0. Okay? We write it in the form of vector. Why in the form of vector? Because the curl of any vector, as this is the curl is always taken as for the vector quantity. So the curl of any vector is a vector quantity. So don't directly write it as 0. As a null vector. Okay, so this one is called as a null vector. Okay, so this is our first identity, that is the curl of gradient of a scalar is a 0. And we have to use these identities later on in our syllabus in some of the theorems. Directly we can use these identities. For this first identity, second identity. That is del cross a vector is equal to 0. This is our second. Del cross a vector is 0, or you can also write it as divergence of curl A vector is equal to 0. Divergence of A vector is always equal to 0, where A is any vector. Okay, here it is a symbol is put down here. So A is any vector. So let's do the proof for this. So starting with the proof, so starting with the curl loss of A vector. We solve this del cross A vector. So with the help of determinant, I'm going to solve it. It is curly by curly x, curly by curly y, curly by curly z. This is my del component. Okay, and for A vector, I am going to write here as ax, ay, and az. Okay, where A vector becomes, I'm simply writing A vector as ax I cap plus ay j cap plus az. Okay, how this vector is represented actually? It has some unit vectors, okay, and some associated magnitudes ax, ay, and az. Okay, so in the form of determinant, it can be written like this, and this will give you I cap just cross multiply, that is curly az by curly y minus curly ay by curly z. Like this. Curly az by curly x minus curly ax by curly z. Okay. And plus k cap curly a, just cross multiply this, ay by curly x minus curly ax curly y. Okay, this is a simple representation for the curve. Okay, now next we have to do the divergence. We have to do the divergence with this curve. Therefore, del dot del cross A vector. Okay, take the divergence of this quantity. So let's do that. What is that? Curly by curly x I cap plus curly by curly y j cap plus curly by curly z k cap. See your del. Okay. You have to do the divergence with del crossing. Okay. So what is del crossing? This one. I'm not writing it again. So this is our del cross A. Okay, just take the divergence with this quantity, and we know that for taking the divergence, we just have to multiply the same unit vector terms. Okay, like this term is multiplied with this term is multiplied with this term is multiplied with this. And we also know that the result for the divergence is a scalar quantity. So no unit vector will be there in this final result. Okay, so let's write it down. Just multiply curly x with this one. I'm just writing it firstly one step. That is curly az by curly y minus curly ay by curly z. Then plus curly by curly y. Here it is negative sign, so keep it here negative. So curly az by curly x minus curly ax by curly z. Like this. Then this one finally plus curly by curly z curly ay by curly x minus curly ax by curly y, like this. It is the next step. So just open the brackets, so it comes out to be curly square az, the first one, curly square az by curly x curly y, like this. Okay, minus curly square ay curly x curly z. Okay, then next minus curly square az by curly x curly y, then plus curly square ax by curly y curly z. Okay, then finally plus curly square ay by curly x curly z minus curly square ax by curly y curly z. Okay, now just see the common terms, like here it is curly square az by curly x curly y with the positive sign and the same quantity with the negative sign also. So cancel out these two. Then curly square ay curly x, here it is with negative sign and here it is with the positive sign. Just cancel it, and finally this term, here it is with positive sign, negative sign, and cancel it. As all the terms cancel each other, okay, positive negative terms are cancel out. So finally, and also this is not a vector quantity. Okay, so we can simply write the answer as 0. Okay, we can simply write the answer as 0, not the null vector. It's the null vector only in the case of first identity, because the output of that one is the vector quantity. But here the output for any divergence is a scalar quantity. Okay, so here the answer comes out to be simply not the null vector. The answer is 0. Okay, so these are the two identities which we have to remember and can be able to do the proofs also. Okay, and these identities will be used later on in the further theorems. Okay, now let's start with the theorem parts, and we have to do the 4 theorems. One is the Gauss Divergence Theorem, then Stokes Theorem, then Green's Theorem, and then Helmholtz Theorem. So let's start with the theorem parts. Okay, now let's start with the theorems part. So these are actually called as integral theorems, and under the theorems we have to cover the 4 theorems like Gauss Divergence Theorem, then Stokes Theorem, then Green's Theorem, and then Helmholtz Theorem. Okay, and Gauss Divergence Theorem and Stokes Theorem are almost similar. Similar steps are going through the proof. And so before starting with the theorems, we have to just a little introduction with some of the terms like line integral, surface integral, and volume integral. Okay, so there are 3 terms. One is line integral. Okay, the line integral, it is represented for like this, dl. Okay, here the notation used is for line, it is dl, that is the integral taken over any simple line or any curve. Okay, if there is the vector is there on any line and integral is taken over that line, so we can call it as the line integral. So sometimes there are margins are also there, like here it is a, here it is b, that is integration from a to b. like this. Some limits may be there, okay, for the line integral. And if the curve is a closed curve, like if the curve is, firstly go here, then go here. If the curve is a closed curve, then for closed curve, the integral can be written like this. A vector dl. dl is used for the line integral. Okay, for closed curve, this symbol is used. This represents the closed curve. And for any vector, if this closed curve is 0, if this one a dl is equal to 0, then we can call that field is a conservative field. Then we called this term as a conservative field. If the line integral for any electric field or any other field is 0, then we called that as the conservative field. Just remember this concept, because we have to use this concept in our derivations of boundary conditions. Okay, so for the conservative field, the line integral of that vector is 0. The second term is surface integral. Surface integral means any surface, like any two-dimensional surface is there. If any surface is there, a two-dimensional surface is there, then this integral is represented like, it is represented by the double integral symbol. Okay, here the double integral is there, a vector ds. Okay, here for surface integral, ds is used and double integral is used. Okay, or you can also write it as a vector ds, or simply write here as s. So this also represents your surface integral. Okay, simply write it here s. Now for the volume integral, the volume integral is taken for the three-dimensional space. So that's why it is also called as the space integral. And it can be, diagram can be drawn like this for a three-dimensional. Okay, for a three-dimensional, so this can be represented with the three integral signs a, d, v. Here it can be written as dv, or you can also write this as a dv and just put it here v. So this also means the volume integral. Okay, this also means volume integral is there. Okay, so these are some of the terms which we are going to use in our the proofs of the theorems. So line integral, surface integral, volume integral. Line integral one-dimensional, surface integral two-dimensional, volume integral three-dimensional. Okay, this is for the simple curve. This is for the any surface, two-dimensional surface, and this is for the space integral, that is the three-dimensional volume. Okay, and these are how to write these integrals. Simply write here s, v, and this one also you can simply write here as l for the line integral. So these are some of the terms. So the Gauss Divergence Theorem. So it states that the volume integral of the divergence of any vector field A vector taken over any volume V. So these A and V are the symbols used here. Taken over any volume V is equal to the surface integral of A vector taken over the closed surface surrounding the volume V. So just read it carefully, that firstly the divergence of A vector is taken and the volume integral of that divergence is done. So on this side, left hand side, it is del dot A vector and with the volume integral. And this is equal to the surface integral of A vector taken over the closed surface. So simply it is the surface integral of A vector. So how this is mathematically represented, the Gauss Divergence Theorem. So this is one is the Gauss Divergence Theorem, and just note it down here like that. Taken over the closed surface surrounding the volume. Here in this theorem, the surface surrounds the volume. Okay, volume is inside and the surface is there on the outside boundary. Okay, so let's start with the proof now. And one thing is just noted down here from that, on the left hand side there is the volume integral, on the right hand side there is the surface integral. Okay, so what is the main application of this theorem? This theorem is used where we have to convert the volume integral into the surface integral, or vice versa. Okay, there are some requirements in which we have to convert the surface into the volume or volume into the surface. Then we can apply this Gauss divergence theorem. So let's start with the proof. So simply starting with the first step, like any volume V, consider any volume V of any shape enclosed by surface S. ठीक है, consider any volume V of any shape enclosed by the surface S. Just draw it like this. Okay. And here it is the volume V. Volume is enclosed by the surface S, and from this volume, two integrals that is diverging, that is the A vector that we have assumed, the A vector. So A vector and the surface ds vector. These are the diverging vectors from this volume. Okay, so we can write it down like this. So the vector diverging from S, vector diverging from S of volume V, from S of volume V is, it can be written as, you can also write here for vector, you can also write as the flux, because the flux lines are diverging. ठीक है, flux, so this can be written as phi is equal to A ds. Okay, here it is the surface integral. Just put down here is A vector into dot ds vector, because here the ds is also a vector that is diverging from this small volume. Okay. So phi is equals to A ds. Now in the next step, now divide the volume into two parts. Volume into two parts, V1 and V2. Dividing the volume into two parts, V1 and V2, enclosed by the surfaces, enclosed by S1 and S2. ठीक है, and just redraw the figure again for this second step, like now in the second step we have to divide this volume. Okay, we set that part as V1 and the second part we set that as the V2, and that are enclosed by the surfaces S1. Here it is V1, here it is V2. V1 is enclosed by S1 and V2 is enclosed by S2. Okay, and this portion, this one, this is the common portion. between both V1 and V2. So we have to write down in the similar way the flux diverging from, therefore flux diverging from S1 of volume V1, like this. Flux diverging from S1 of volume V1, so it can be written like A vector ds1. Here it is now S1. We can write the same now in the two steps. And the flux diverging from S2 of volume V2, it is equal to A vector ds2, here it is S2. Okay, so these are the steps when the volume is divided into two parts. And here you have seen that the shaded portion is common between V1 and V2. So the flux diverging from here, it is here, and from here, it cancel out each other. So we are not to consider the flux diverging on this shaded portion, because as both these fluxes cancel out each other, so we are simply write down in these two steps. Okay, therefore the flux emerging out of the shaded portion is being equal and opposite in direction, therefore cancel out each other, and hence the net flux phi, therefore the net flux phi is equal to, that is A ds, it is equal to A1, sorry, A ds1, here it is S1, plus S2 A ds2. This is the net flux, that is the sum of these two fluxes. Okay, and now in the next step, we are going to divide this volume into the large number of parts. Okay, firstly we have taken a single volume, then we divide that volume into the two parts, and in the next step we are going to divide the volume into the large number of parts. So how to divide that volume? Like, just divide this volume into the large number of parts. Let us say n parts will be there. Okay, V1, V2, V3 up to Vn, that are enclosed by the large number of surfaces also, like S1, S2, S3 and up to Sn. So simply, and just write it down like, now similarly, if we divide the volume into large number of parts, if we divide the volume into the large number of parts, that is V1, V2, V3 up to Vn, enclosed by S1, S2 up to Sn. Okay, then the net flux, then net flux phi, in the similar way as we have done in the previous step, so it can also be written as phi is equals to A ds, that is equal to S1 A ds1 plus S2 A ds2 plus S3 A ds3 and so on Sn ADS N. So in this way it can be written. Okay, and if we put down here the summation sign, this can be written as with the summation sign, that is I is equals to 1 to n. So it can be written as SI ADS I. Okay, so this is how it is written in the form of summations. Now in the next step, divide and multiply by Vi. Okay, in the next step, divide and multiply by Vi. Now here, divide and multiply by Vi. Multiply it with Vi, no? So this will comes out to be this. Therefore, ADS is equal to, simply multiply and divide this term by Vi. So this can be written as summation of I is equal to 1 to n Vi into ADSI divided by, here it is again SI, by Vi. Okay, what we do? We divide and multiply this term by Vi. Divide and multiply this term by Vi. Okay, and just mark this as equation number 1. And what do we observe here? That as the number of parts of that volume are increasing, so that volume reduces its size. Okay, when the volume is in the single part, it is a big volume. When we divide that volume into 2 parts, its size reduces. Okay, further, when we divide that volume into n parts, its size further reduces. So, if now here we are going to apply the limit. Okay, if n tends to infinity, n tends to infinity means if the number of volumes are increasing. Okay, if n tends to infinity, v tends to 0. जैसे जैसे parts increase होते जाएंगे, the volume, the size of the volume reduces. So if n tends to infinity, v tends to 0. And now we have to apply this limit here. Now I am going to apply the limit here. So therefore, limit, in this way I am going to represent the limit, or you can simply write here LM, or full write down the limit. Okay, so limit Vi tends to 0 and over this ADSI, here it is SI upon Vi. I am going to apply this limit on the flux diverging over the volume V. Only upon this quantity, that is a flux diverging over the volume V, and this limit represents your divergence. This is the actual representation of divergence, that is flux diverging over the volume V. Okay, so this represents your divergence. Okay, mark it as equation number 2. And also now converting summation into integration. So there is also the formula which converts the summation into integration. So this summation sign with the volume V, it can be simply converted into the integration. Okay, this summation, that is summation of Vi, I tends from 1 to n. So this is converted into integration simply like dV. Okay, so mark this as equation number 3. Now from 1, 2 and 3. Now from 1, 2 and 3, or you can simply put 2 and 3 in 1 in the next step. 2 and 3 in 1. 2 and 3 in 1. So what we got here now, that is on this left hand side it is a ds surface integral of a vector, it is equal to, so this term represents your divergence and this represents your integral, volume integral, because the summation is of the volume. Okay, and that summation of volume is converted into the volume integral. And so this can be combined, it can be written as del dot a vector d. Okay, and this is the final proof for Gauss Divergence Theorem. Okay, here is the divergence. So it is used to convert. It is used to convert surface integral into volume integral, surface integral into volume integral, and vice versa. That means the volume integral can be converted into the surface integral, or surface integral is converted into the volume integral. So this is the usage for the Gauss Divergence Theorem. And this is the final result that we have proved. So this one is hence proved. Okay, so this is the finally Gauss Divergence Theorem. This is all about today's lecture, and today we have covered 2 identities and 1 theorem. The proof of 2 identities, the first one is the curve of the gradient of any scalar is 0, and the second one is the divergence of the curve of any vector is 0. And one theorem we have covered, that is the Gauss divergence theorem, that is used to convert the surface